Yep, you read that right. State machine is done. Stop using them. You gotta find some other solutions. That's the video. Goodbye and good luck. Well, obviously that's a little bit of an exaggeration, but you clicked on this video because you know there is a limitation that you're feeling in the finite state machine, or maybe you haven't experienced it, but you have heard of the issues. Our use cases have outgrown them as it is. So let's talk about why they fall apart and also some alternative solutions to replace them. Well, specifically, we're going to talk about 5 different alternatives. Okay, so let's talk about our finite state machine. So finite state machine comes with these like states to start. You have something like idle. Sorry for the bad drawing, but this will do the job. You have run state, and then you have a jump state, for example. And then for each state, we have some animations or actions that gets played. And we want to figure out some transitions. So from idle, we go to jump. If player clicks a jump button, and then from jump, we can go to run. If player starts running with their arrow key, and then we go back to idle when player stops inputting. But then again, it's not done, right? From run, players can also jump by clicking a jump button. So now we have when jump button gets pressed from either of the states, we go to the jump. And if the run button gets pressed from idle or jump, we can go back to the run. When the jump is done, we go back to idle and nothing is pressed, right? Or is this true? Because if we're in the middle of the air, can we run in the middle of the air? Or do we have to wait? So it'll be like, oh, if jump is done and we're moving, then we can transition to run. Well, either way, you can kind of see how like for each of the states we're making, we're essentially connecting all of them anyways. And the additional complication happens when we start talking about other complex mechanic that is present in every game. And it doesn't have to be a game. We're using game as an example because, my channel is about game development. But yeah, so if we take a look at this, what happens next? We may get something like, oh, what if you add a dash? If we add a dash, now we're thinking about, okay, can we go from idle to dash? Yeah, we can go from idle to dash as long as we press the dash button. Can we go from run to dash? Yes, we can go to run to dash. And then from dash, can you jump? Maybe not, but can you run? Yes, you can transition to run. You can transition to idle by stop moving. What if you have a stun lock? The enemy can hit your character and then all of a sudden you get stunned and you don't want any other things to happen while being stunned. So you're like, oh, if from any of these states, if the enemy hits you, all of a sudden you can get stunned from anywhere. While stunned, you don't do anything. And then maybe you go back to the idle, but then what if you're like stunned in the mid jump? So you have this like transitional state that says in air stun. I mean, you can already see there are mess of lines forming into a bowl of unhandleable spaghetti of state machine, right? Clearly, in the context of complex states, we have issues. And this is called a state explosion, right? This one particular issue because there are so many possibilities, so many states we can potentially define. And, this might be a design problem. It's not inherently a state problem. That's why first 2 things we're going to talk about is more of a improvement on the vanilla state machine to make it more manageable. And then the last 3 will go out of the state machine kind of design. There's some similarities. It's out there enough that it feels like its own thing. So stick around. Those are really important. This is important too. So the first thing I want to talk about is that state explosion. Can we still use our finite state machine and avoid the state explosion? As you probably can see from this example, main issue is that there are complex combination of states that are represented by a single state machine. And so, the natural thought that we all go through is to create multiple state machines for different pieces and combining them together. That works. But also sometimes you do just need a single state machine with a lot of states. But maybe some of those states are categorized as a group. And that's where we come up with the idea of hierarchical state machine. The name is pretty obvious to kind of give you an idea of what that might be, and you might have already heard it. When we go back to our old example of going from idle to run, instead of going to run, we could go into something like move, for example. So we can say, hey, idle to move just means the velocity is greater than 0. And then the move, if we expand the move out, let's say this is the move state, we may have something like run, walk, dash, I don't know, slide, cancel, it doesn't matter. And they may have their own relationship, and you're only containing your states within this move state. And once you go out of it, you're out of it. This helps with organizing it, and this helps with kind of categorizing each of the states into more manageable sections so that your state diagram looks simpler. So that's one option. I know conceptually is very simple. There are some additional things you need to consider when implementing this, and that's why I'm also releasing a video of me implementing all the solutions that I talk about here in Godot specifically, but I will also be live coding it in the next video to show how I did it in case you're not using it in Godot. So that's first one. Now that's just considering the downside of a state explosion within the state machine. Let's say we have something like this. We have a jump, and then we have a idle, and then we have a sit, for example. What if sit is a toggle? So we say, okay, idle, we're going to toggle something, and then we are sitting down now. User is not inputting. We don't really go back to idle until something has been pressed again. We're not holding buttons. It doesn't really matter. So from sitting, user presses a jump button, and then you jump. And then when the jump is done, where should it go back to? For my game, if I'm sitting down and jumping, when the jump is done, I want to go back to sitting automatically. Or if you're standing up, and then you jump and you land, I want to go back to standing up. I mean, this is a kind of silly example, but actual example might be like when an AI is shooting a gun, right? You can say, oh, shooting a gun makes it so that the arm animation goes like this, and then it shoots. And when it's done, it shouldn't stand up. If you're squatting and shooting, it should go back to squatting. If you're standing up and shooting, when shooting is done, you should go back to standing. So there are cases where a single state needs to auto-transition back to a previous state. And thing about the vanilla state machine is that they don't keep track of history because they're just providing a very specific state as a transition target. And so what we call, I think it's popularized as a push-down automata, which sounds fancy. It just means let's keep a stack of states as a history. So for example, keep track of this state history. And whenever we're transitioning the state, we're going to keep it into a stack. So for example, we start at idle. So idle gets pushed into a stack, right? It just goes in here. So we're in idle. And then we go back to jump, or not go back, but we transition to jump. On top of this stack, a jump gets added. Sorry for this like misalignment. I'm sure this bothers some people. So when it's time to go back to transition, instead of saying, hey, jump, you decide exactly what it's going to transition to. It just says, hey, pop the stack and, go back to whatever is on top of the stack. That means at the end of the jump, we're going to pop the stack, meaning we're popping it from the top. It's like stack is a tray that's stacked on top of each other. So we're taking the top out. So jump will be taken out on pop. And then now we're at idle, so we go back to the idle. And it's the same example if sit is at the bottom. So this stack-based state machine or push-down automata would be used for history keeping. And this is actually very useful in making sure there are some natural flow where you don't have to worry about these transitioning back. You can kind of describe this as previous, whatever that may be. And, in the design itself, we don't have to worry about like drawing everything to make our design so complicated. So yeah, those are two really powerful upgrades, powerful and simple upgrades you can make to your state machine to solve some of the pain point of your finite state machine. All right, so it's time to really leave the state machine world completely. The state machine does a great job of defining a state and then deciding what that looks like. It's very singular. But as soon as we get into these like complex behavior as opposed to a state, it becomes a little bit more puzzling. For example, if we say we're going to have an enemy character AI that needs to scan for a player and then go out there, and when they find the player, chase them. And then when they are in range, attack them. That's a sequence of event that needs to happen as opposed to just being a state machine. Now, technically, you could have a separate state machine just for behavior, but it's less of like it can go from state to state. It's more of like behavioral failure. For example, if I go, oh, do I see a player around me? No, then move around. Yes, then chase them. That kind of logic is more of a decision tree than a state machine. In game development and robotics, people start to use something called a behavioral tree or behavior tree, not behavioral tree. It's what it sounds like. It's a tree of behavior, but it's a little bit more complicated than that. It's not just deciding, go down the tree and do the things that it tells you to do. There are a few concepts that we need to talk about. Okay, so in a behavior tree, you might have these like nodes and series until you get these like leaves. And each of these nodes are some actions or series of actions. And what we have is at the leaf are the actions. For example, like run, shoot, unlock, open. Those things would be here. Each of these nodes can be two different things. It can either be a selector or a sequence. The whole concept is that in behavior tree, you do execute these actions one at a time in order, right? So if we have a selector, for example, this is a selector, right? That means it's going to go down. It's going to say, hey, do something. And if it fails, it moves on to the next behavior until one of them succeeds. So for example, if the first action fails and then the next action succeeds, then this selector has completed its job. It's going to say, hey, me as a selector succeeded my job. So it's going to go back and say true. And it's going to ignore the last ones, even though it might be successful in the sequence. Where would the selector be used? So for example, let's say we have a recon behavior, and then we use a selector. And then we're going to say have one action where we have chase. And then the next one might be find. In this case, what happens is that first it's going to try to chase something, but it may fail because it's like, well, I have nothing to chase or somebody's out of vision. So it's going to say fail. So if it fails, we're going to go look for find, where it's going to do the finding action, whatever that may be, right? And eventually you loop enough and the find becomes successful, you're going to come to the chase, and instead of trying to find another target, it's going to just chase and be done with it for recon action. So this is a useful fallback mechanism that is the selector. Okay, let's talk about the sequence. Sequence is similar to selector, where you're executing the actions one at a time. Each nodes are executed one at a time. But as the name suggests, instead of being a fallback, it keeps on executing. Good example might be, taking cover. So when you're taking cover, what do you want to do? You want to run to the cover and then maybe return fire because, you want to keep yourself safe, and then run back again. So even if you get blocked in a run, or even if you are trying to return fire and then you're out of ammo, you shouldn't stop running. You should go back to running, or whatever order this is. So this is when the sequence is useful. I mean, there are definitely better examples, but that's it. So behavior tree is this, basically. It's a series of actions and nodes where you can either have a fallback mechanism or just sequence mechanism, and then it's a series of it forming a single behavior. Something that you probably noticed from all the solutions so far are very like one-dimensional. They are just execute and go. Even the state machine is very definite, where they just go, well, here's a transition you need to do, so you do the transition. And obviously there are some like flavors you can do to make it a little bit more random, or even have some sort of priority. And this next kind of concept is more of a design concept than a solution, and it's called utility AI. I don't know who popularized it. I'm sure you can find it. Maybe I could find it. Maybe I should have done that research. But it's basically deciding between two actions based on priority. Between the two actions you have, given the state, priority is determined. So for example, if I'm saying, hey, my health is low, so I'm going to run away, but also my ammo is low, so I need to reload. Now we have two conditions. In a traditional state machine, you might get a case where because two conditions are satisfied, you might get a rapid transition between reload and take cover. When it's trying to take cover, it sees that the ammo is low and then it goes to reload. And when it's in the reload state, it sees that the health is low, so it goes to take cover. Now, obviously, you can try to solve this by adding delays to the state, some randomness to the state, but it's still not satisfying. You still get this like little twitch state action. And even if you make it into a decision tree, you're always prioritizing one over the other. What if health is not that urgent? You're just hurt a little bit. And depending on what that is, what if there are other actions that you need to prioritize over this? So this is where utility AI becomes useful. Conceptually, what it is that it's just, as I said before, it's just deciding priority based on the state of the character, game, the state of the world that the program lives in. If the priority of taking cover is proportionate or inversely proportionate to the health, so lower the health goes, closer to priority 1, the take cover becomes. And then ammo could have some sort of like flat priority of 0.5. So then you get this situation of as the health gets lower and lower, at some point, taking cover becomes more important than reloading. Obviously, this can be implemented in many ways. And there's no diagram for this one in particular because you can probably imagine how this can be used in both decision tree and state machine. So think about it. We already had a decision tree where we have an action and we have some sort of like selector or sequence, right? And then the thing about the selector and then the sequence was that when it has its children, they execute through the available actions in order. The alternative, if we're applying the concept of utility AI, is for these actions, each of the actions, to have its own priority calculation. Instead of just getting all the children and going through them one at a time, you can pop that into a priority queue based on their priority and then do it in the order of priority as opposed to in the order of whatever was designed. So then that's an easy way to implement this utility AI in addition to decision tree. Now, if you don't need a full-on decision tree and it's a simple matter of choosing A or B, you could also have this like spread. And I've actually personally implemented this in some of the conversational design thing. You know, those cases where like NPCs in the game has something to say about the situation and it feels natural. And the way that works is basically utility AI. So let's say you have a flat table of bunch of dialogues, and depending on the situation, you could have, hey, say, go away, or I don't know. I mean, that's a bad idea. Let's do take cover versus incoming fire or whatever, right? Or fire in the hole, that kind of stuff. And you want them to say these things, and you can have a condition that would allow this. So each of these dialogue might have a condition tied to them. So first of all, given the world states, you reduce it down to fewer dialogues, right? You have like D1, D10, whatever. And then from these reduced option of dialogues, given the state, they may have a built-in priority 1, 2, 3. And what that would do is that it would organize it based on the urgency of the dialogue. And then if you just have some sort of weighted randomness, you get this like natural conversational feel to the game. And that would be considered utility AI in some ways. I mean, this is like a little bit of stretch, but you know, I guess technically instead of 5 things, we're talking about 6 things because this is like just enough like differentiation that I can't quite include it with utility AI, but it's conceptually utility AI. And as I'm saying this, what I'm realizing and what you should realize is that any of these concepts are just that. It's concepts and design patterns. You can apply them however you want. There are so many solutions, so many ways to implement this. So don't get caught up by what I'm describing or what people are describing online in general, and try to be creative with it. And obviously, you know, you can take some guidance from tutorial. Low key, high key, advertising a tutorial, which I'm going to release. So do watch that, but make sure to have your critical thinking cap on. So what if we want to design something like Sims or Dwarf Fortress, where each of the NPCs decide what they want to do or what they should do based on their goal? And that's where planning ahead as a concept becomes big. It sounds magical. It almost sounds like Gen AI thing. It's not. Let's go back to that example of NPC getting low on health, right? And then we said, hey, when you're low on health, priority of taking cover is higher and reloading is lower. Instead of saying taking cover, what if we give them a goal? Instead of asking what to do, they're asking what is the goal of the situation. And that is what we call a goal-oriented action planning, GOAP for short. It's actually a known thing. It's actually a thing. Go look it up. It's a real thing. I didn't make this up. There's some interesting, elegant solution to that, which can be a little bit difficult to implement, but conceptually it's very interesting. So instead, when you're falling low in your health, instead of taking cover, or instead of just using the med kit, the NPC could decide, I want the goal of achieving higher health. So that is just saying, hey, I want the state of health to be higher. How do I do that? What we do in goal action planning is basically a little bit like a pathfinding within the available actions. I'm going to grossly oversimplify this for the sake of explanation, but think about this. So let's say you have a starting point where the state health is like at, 10, let's say, and we want to go to 100. So we say, hey, I want the goal state equals HP, greater than 50. Let's say that's my goal. Then we look through all the available action for this particular NPCs, right? Stuff like move to rock, fire, crawl, or, hide, whatever. Let's say this is some examples. And then basically we can have either depending on how you implement the state, you can have something like a star. I'm going to go for a Dijkstra's algorithm where it does breadth first search, right? And if you go through each of these available action, you get a resulting state, right? Because each of these actions changes the NPC's state in this world. It impacts the world. So when you go to move to rock, it might say, hey, position becomes, X and Y. This one might say ammo goes down, where ammo is lower. Enemy health becomes lower, let's say, for example. The whole concept is that each action on this planning stage have something called a precondition and a postcondition. Can you guess what this means? I'm pretty sure you can guess it. Well, I just explained through the example, so you should probably be able to guess. So each of the action has something called a precondition, which is a condition for these actions to be available. Move to the rock is not available if there is no rock in the vicinity, right? Firing a gun is not a possible action if there's no target to fire to. I guess it really depends on the game. I guess you can fire in the air, but that's besides the point. So you are reducing the number of actions that you are looking through this precondition. And then after the action has been executed, the state changes. So we have a postcondition. So we can pre-calculate that and say, hey, well, if you do this action, this will become the state of it. And can you see what happens next? After this, I think this feels elegant in terms of solution, as far as the solution is concerned. Because once you have each of the action and you say potentially, if I pretend that these actions have been executed, we have a resulting state that are different, right? We have state 1, state 2, and state 3. And based on these states, we have more actions available, filtered by the preconditions. So preconditions based on this state will be our available actions. And then we go. And eventually you get this like path within the action graph where finally you have a state where goal is reached. Post condition of this state, let's say, is a med kit. Somehow we got to a med kit use, and then now HP is greater than 50. So now it's going to say, hey, I found a way to do it. Go take cover, look for medkit, pick a medkit, use medkit, and then your HP is 50. And this could go with a lot of other things. For example, if I say take revenge on blah, 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 that could be an interesting one. What does that mean? Take revenge means I want the goal state to be this target to die, but I don't know where this target is. So then there's this like whole story that can be built like Dwarf Fortress, where you have a situation, this character is going through different places to find this person and take revenge. Interesting, right? I think it has a lot of potential. And this one, I think, is my favorite solution, which I haven't personally used yet, that I'm trying to use, especially because I'm really, really interested in procedural narratives. And that's something that I think could be really fun. Let me know if you can think of your own way to implement this in your game. Also, a lot of these are just concepts. I would love to hear what you think would be useful in your own game. Maybe finite state machine is just fine for you, or maybe one of these things that I've talked about is really helpful for you as well. But ultimately, as you can probably tell, not one is a solution for all. For the most part, you want to use a mix of everything in some sense. And I can already think of some ways that I need to mix it. We talked about utility AI being used with decision tree, right? Just be creative with it and explore these options. But please, stop using just normal vanilla state machine and be stubborn with it, especially when you're getting this state explosion. You're going to have a bad time. On the next series, I'm going to actually manually implement this and show how to do it, at least in my own flavor. I like to do my tutorial in live coding with minimal editing. So if that's something you're into, subscribe and follow so you can get that in the future. Otherwise, that's it for today. Thanks for watching. Goodbye.